for you today, string theory. And I got to give a huge shout out to you, our listeners, because you absolutely flooded my inbox with articles and research on this one. So let's get
Yeah.
right into it.
It's definitely exciting stuff. String theory is really ambitious, trying to take on this huge challenge, unifying all four fundamental forces of nature. We're talking gravity, electromagnetism, strong and weak nuclear forces, all in one framework. And physicists have been struggling with this for ages, right? Like, how do you get Einstein's theory of gravity, which is general relativity, to play nice with quantum mechanics that governs the other three forces on those tiny scales? And it's like they speak different languages. But string theory, it might just be the translator we need.
Okay, so I think a lot of us, when we picture the universe, it's like we imagine these tiny little billiard balls, right? Those indivisible particles making up everything. But string theory says, nope, scratch that. We're talking super tiny vibrating strings instead. And this is where things get really cool. It's like, think of a guitar string. Different vibrations give you different notes. Well, in string theory, those vibrations, they create different particles, electrons, quarks, even those mysterious gravitons.
Exactly. And here's where it gets even more mind-blowing. String theory needs more than just the three dimensions we experience every day. To make the math actually work, you got to have these extra hidden dimensions, maybe 6, maybe even 7 more, and they're all curled up like super tight so we can't see them directly. Think of it like, have you ever rolled up a piece of paper so small it just looks like a line? That's kind of what's going on here.
Oh, okay, so these extra dimensions, like they're the hidden folds of reality itself.
Yeah.
So tell me, what do they look like? I mean, can we even picture these things?
Well, the idea is they take these super complex, multidimensional shapes, we call them Calabi-Yau manifolds, and, they're not just mathematically beautiful, their shape and symmetry are actually key to how those strings vibrate and ultimately how all the properties of those particles are determined.
Calabi-Yau manifolds?
Yeah.
Okay, I'm going to need some time to wrap my head around that one.
Right.
But you were talking about unifying those forces before, so how does string theory actually pull that off?
Well, it basically proposes that all four of those forces, they're all just different expressions of one underlying force, the vibration of those tiny strings. It's like different sides of the same coin. And if string theory is right, it would completely revolutionize our understanding of the universe. It'd be the single, elegant framework that explains, well, everything.
That would be huge. And I know from all the articles you sent, string theory has some really wild things to say about black holes, too.
Oh, definitely.
Let's get into that.
So black holes, they're these areas in space-time where gravity is just insanely intense. Nothing escapes, not even light. But string theory, it suggests that information about whatever falls into a black hole, it doesn't just disappear. It gets, encoded on its surface, the event horizon, the point of no return.
So it's like the information is, plastered onto the black hole surface.
Yeah, that's a good way to think about it. And this ties into something called the holographic principle. It suggests that our 3D universe, what we see and experience, might actually just be a projection from a 2D surface, like a hologram.
So we could be living in a giant cosmic hologram. Okay, officially mind blown. This is heavy stuff.
Okay.
But you're doing a great job explaining it. I'm really starting to get a sense of just how profound all this is.
Yeah, it's definitely mind-bending. And keep in mind, all these ideas are still theoretical. We haven't experimentally proven them yet. And speaking of that, before we go any further, we should probably talk about the different types of string theory out there. It's not just one neat theory. It's actually more like a family.
Oh, things are about to get even more interesting. So lay it on me. What are these different flavors of string theory? A whole family of theories. Wow. Okay, so what are we talking about here? How many string theories are there?
Well, there are 5 main types, and they each have their own unique way of describing those vibrating strings and those extra dimensions we talked about. You got type I, type IIA, type IIB, and then 2 types of heterotic string theory.
Okay, 5 main types. So what are the big differences between them?
Well, type I, that one's unique because it includes both open strings, which have endpoints, and closed strings that make loops. The other 4, they just deal with closed strings. And then you've got type IA and IIB. Those 2 differ in how they handle something called chirality.
Chirality, okay, that's a new one.
Yeah, it's a property of particles that determines how they interact with the weak nuclear force. Imagine you're trying to shake someone's hand, right? And you use your left hand, but they're extending their right. It's just not going to work. So particles with different chirality, they interact differently, kind of like that. And then the heterotic theories, those are pretty fascinating. They combine elements of superstring theory, which incorporates supersymmetry, and bosonic string theory, which is a whole other beast. It's like they blend different theoretical lineages to create a new hybrid.
Okay, so we got open strings, closed strings, chirality, different theories. This is getting pretty complex. Is there some way to, like, bring it all together? I remember from the articles you sent, there was something called M theory.
Exactly. You're totally on the right track. With all these variations, it does seem like a bit of a mess. But that's where M theory comes in. It's a potential framework for unifying all five of those string theories.
Okay, so M theory, it's like the grand unifier. But how does it actually, do that? How does it bring all those theories together?
Well, the big thing with M theory is that it brings in another dimension, an 11th dimension, to be precise. And it suggests that all five string theories, they're actually just different perspectives of the same fundamental reality. Like, imagine looking at a sculpture from different angles. Each view is unique, but it's still the same sculpture.
11 dimensions. Okay, my brain's definitely starting to hurt now. But, one thing that keeps coming up with string theory is this idea of supersymmetry, or SUSY. What are those superpartner particles everyone's so excited about?
Ah, yes, supersymmetry. It's a key concept in string theory, and it basically proposes that every known particle has a superpartner particle, a twin, if you will, with slightly different properties. So, like, for every electron, there'd be a selectron, for every quark, a squark.
So it's like there's a whole hidden world of particles mirroring our own.
Exactly. And these superpartners could be the answer to some of the biggest mysteries in physics, like dark matter. Some physicists believe that the lightest superpartner particle, that could be the dark matter particle we've been searching for.
Wow. So finding these superpartners, that would be a huge deal, both for string theory and for our understanding of, well, the universe. But are we even close? I mean, can we detect these superpartners?
Well, that's the tricky part. Our current particle accelerators, like the Large Hadron Collider, they're just not powerful enough to reach the energy levels we need to create these superpartners. It's like trying to find a needle in a cosmic haystack.
So we need a much bigger, much more powerful collider to crack this mystery. But while the search for superpartners continues, let's talk about some of the challenges that string theory faces. I know it's not all smooth sailing, right? There are some criticisms out there.
Yeah, you're right. No scientific theory is perfect, and string theory definitely has its share of challenges. One of the biggest ones is that it's really, really hard to test experimentally. Those strings are so incredibly tiny, and the energies needed to study them are just immense. So we're not even close to being able to observe them directly.
So it's mostly a mathematical framework for now.
Yeah, pretty much. And that leads some critics to argue that it's too speculative, too removed from, actually being able to prove it. They say a theory you can't test, it's more like philosophy than science.
I see their point. So how do string theorists respond to that?
Well, they acknowledge the difficulties, but they argue that, even though we can't directly observe these strings yet, string theory has already given us some really valuable insights and connections within physics. It's a work in progress, and they believe that as technology gets better, we will eventually be able to test some of its predictions.
So it's a waiting game for now.
In a sense, yeah. But even if string theory doesn't turn out to be the theory of everything, just exploring it has really deepened our understanding of physics. And there's one more really important aspect we need to talk about, the landscape problem. It comes up when you try to use string theory to explain the vastness and diversity of the cosmos, and it gets pretty wild.
Okay, the landscape problem. That sounds ominous. Tell me more. The landscape problem, huh? Okay, so string theory might be leading us into some pretty uncharted territory here.
Yeah, you could say that. It's this issue that arises because string theory, in trying to be a theory of everything, it doesn't just predict one universe. It predicts a huge number of possible universes, like an insane amount. And each one would have its own unique set of physical laws and constants.
Whoa. Okay, so instead of just one universe, we might be talking about a whole multiverse with tons of universes, each having its own reality.
It's a wild idea. Think of it like a landscape, but like a cosmic landscape with countless valleys. And each valley represents a different universe with its own special properties. Some might be similar to ours, with stars and galaxies and stuff, but others could be totally different, maybe with forces we can't even imagine.
Wow, that's a lot to take in. So where does our universe fit into all of this? Like, does string theory tell us why our universe is the way it is?
Well, that's the heart of the landscape problem. String theory doesn't really give us a clear way to figure out why our universe has the specific properties we see. It's like we're stuck in this one particular valley in the cosmic landscape, but we have no idea how we got here or why this valley is our home.
So that's a pretty big challenge for string theory. How are physicists even starting to try and, like, solve this landscape problem?
Well, there are a couple of ways they're approaching it. Some are trying to find ways to narrow down the number of possible universes. They're looking for some fundamental principles or symmetries that could explain why our universe has the properties it does, like finding the blueprint, the design that shaped this whole cosmic landscape.
So it's kind of like looking for the cosmic architect who designed the multiverse.
Haha, yeah, something like that. But then other physicists, they're exploring the idea that maybe all those different universes actually exist. Like we're just one bubble in this vast, almost like a frothing multiverse with tons of other universes bubbling up all around us.
Wow, that's incredible. So string theory, it might not just be a theory of everything, but a theory of everything everywhere.
It's a pretty amazing possibility, and it brings up all sorts of philosophical questions, like what is reality? How much of it is just chance? And what is our place in all of this?
I think my brain is officially full. We've covered so much, from these tiny vibrating strings to this mind-blowing multiverse. It's been a really amazing journey exploring the mysteries and challenges of string theory.
Definitely. And even though string theory is still a work in progress, it's really changed how we think about the universe, and it's pushed the boundaries of what we know.
Yeah, it's been incredible. And a huge thanks to you, our listener, for sending all those amazing articles and research. It's your curiosity that makes these deep dives possible.
Absolutely. And don't stop exploring. Keep asking those questions, keep learning, keep looking for those connections that weave together the fabric of reality.
What a great way to wrap things up. We hope you enjoyed this deep dive into string theory. We'll be back soon with another one. Until then, stay curious and keep on diving.